Now we will apply this isotonic calibrations model when the calibrations plot actually does not look like a sigmoidal functions. On those cases, we have applied the isotonic calibrations. Now, in this video, we have seen how to plot this. What is this isotonic calibrations and how to apply it in details we have seen. And so the first thing, first thing we have to apply the isotonic calibrations when our calibration. So calibration. When calibration plot does not look like a sigmoidal function. This is the simple conditions. When our does not its look a sigmoidal functions, on this simple case we will apply the isotonic. Now let's see to this just that I have already discussed in. Postulate. This is the our this axis is denoted the simple average of this simple is average of y hat I. This is the average value of the predicted yi in a chunk, and this axis is the average of average value of yi predicted. It means actually original means another kind you can think is a probability value of you can probability value of yi is equals to 1 for a given xi. This we have already said this thing. Now, if you remember in just previous video, we have seen the real world data are actually look like this type. This type of plot we will got. It's not a sigmoidal type of functions. This type of functions. If you remember this YOLO, like the just YOLO plot that we have taken here, this plot are seen by the black color. Just if you remember this previous plot. Okay, these are actually a calibration empirical plot that we have got. It's actual plot. It's not a sigmoidal functions. Look like this. If we use the Platts calibrations or simple the sigmoidal calibrations, then you got this type of plot. Then you got this type of plot. If you simple apply onto it, means this kind of. It's not look like this. It will be look like this type of calibration. If we simple apply the sigmoidal, it will be look like this. Then there have some error. These portions, there have some error. So this plot is called the Platts calibration. In previous video, we have seen it in detail. These things are called the Platt calibrations. This YOLO are actual empirical plot. Actual plot. This one is the okay. Now, how to find these things? How to find this plot? By simple using means using the some sample technique. Okay. So at the end of the day, what we have to do? At the end of the day, we have to find a functions. We have to find a functions. Since it's a simple type of regression problem, at the end of the day, we have to find a functions like g, g, for this input. This input, this will predict that this output. What will be the value? These jobs that we have to do here, means you can think like a regression problem. That's the G we have to predict. This G actually we have to predict. This G we have to predict. That's the simple job we have to do. This is called the calibration functions. That's the simple thing. Okay. And these things are coming from the decalibration solid. We have seen this thing. Now let's see how we will find this kind of, what is this isotonic calibrations. It is simple. Just try to understand through this picture. Here, let's plot the picture first. Okay. So in this picture, the x-axis is the average of y hat I. This axis is the average of yi. Okay. Now the plot that we have got look like this type. Actual plot actually look like this type. This type of plot we got. This is the actual plot. And if you apply these things, then we call this kind of. But the isotonic calibrations are actually want to predict and to break the whole regions into small chunks, some small portions. Small portions means just first you will break this whole YQ into this type to extend it. So just from here to here, first it will break here, then it will find here, break here, then it will break from here to here, then it will break from here to here, then it will break it. Just this simple job that, and we have to, after breaking this, they have to apply the linear regressions onto it. Let's see, here we have applied the linear regressions. Here first we apply on this portion. Suppose let its value is 1 and its value is 5. It is 7. Suppose let it's 10. It's 11 and it's let 16. Okay. So first it will break the whole portions into small portions like that, and it apply the linear regressions onto it. So on 1 to 5, it will first linear regressions apply on these regions. Now after these regions 5 to 7, they have applied these linear regressions. On 7 to 10, it will apply linear regressions. On 10 to 11, it will apply the linear regression. Similarly, 10 to 6, 11 to 16, it will apply this linear regression. This simple thing that actually internally applied in calibration model. Okay, so this called let this is a line 1, L1, it's L2, it's L3, L4, L5. It's L5. That's the simple. So if you think a straight line, for drawing for find a straight line, we need two parameters. One is M and another one is B. We have already seen this thing. So to predict straight line, y is equals to mx plus b. For a straight line, M and B are the hyperparameter is 2. The hyperparameter for a straight line, we have already known this thing. So the main job in the isotonic regressions is we have to find the M and B in edge regions. In these regions, we have to find M and B. Suppose we have to find M1, B1. In these regions, we have to find M2, B2. In these regions, we have to find M3, B3. Here we have to find M4, B4. Similarly here also M5, B5. That's the simple thing that we have to do. Okay. So the simple job that in isotonic regressions we are going to do, in isotonic regression we have to find some piecewise linear model. Just say it is a linear, but it is piecewise. We have to break the whole regions into small portions. So it is called the piecewise linear model. This thing is called the piecewise linear model. Okay. So here, here we have actually this data we have given. Based on this data, we have to predict this value. So at the end of the day, we have this data. At the end of the day, we have the data look like this. IQ at on this data. On this data, we have to find a calibration model. Calibration model that will predict this value. I so I means the probability of it will predict the probability of q is equals to 1 for a given xq. That is the thing that we have to predict. That's the job that we have to do. So the first thing, the YQ, first thing that we have to do, first we have to break. First we have to break these regions. First we have to break these regions into part. In this part, in this part, in this part, and in this part. So in these regions, it will break into YQ hat. We have break into these two portions, 1 to 5. In these regions, similarly, in these regions, we will break this YQ hat into 5 to 7. Similarly, here also, we will break these regions 7 to 10. Here also, similarly, we have to break it like that. Like first, we have to break the whole regions into small portions. The questions is here, this value that we have got here 1, 5, 7, 10, 11, 16. These values are called the threshold value. How we will find this threshold value? How we will build this? After finding this threshold value, it will be easy to apply the linear model onto it. But the main question is how we will, these things are called the threshold value. These things are called the threshold value. Threshold. Solely. Okay, I am doing some mistake. If you are doing some spelling mistake, please correct it on your. And this is the threshold value. In simple, I am writing it. This is the simple threshold. THR. This is the threshold value. Now the questions that come into our mind, questions that how we will find, how we will find the right threshold value. What will be the right threshold value? How we will find this thing? So that the core idea onto it. Core idea is by simple solving the optimization problem. Let's see how we will find it. The core idea behind this thing. core idea is by solving the optimizations problem. So we have to find the, suppose let it's the A1, suppose let the A1, it's A2, it's A3, it's A4, A5, and it's A6. This is the threshold value. You have to predict this. So, so to, to find the threshold value like A1 up to something. So after finding this, then we can easily apply the sublinear model onto it. So on these regions we have applied L1. On these regions we can apply L2. On these regions we can apply L3, L4, L5, like that. You can apply it linear model. And for this linear model, for this age linear model, we can we have to find this value. It's M1, B1, M2, B2, M3, B3, similarly for M4, B4. Similarly here we have to find M5, B5. We have to find these values for age line, for age linear model. So the simple, this concept is, core idea is, we have applied here the extended linear regression. Okay, so here we apply the simple, here we apply the extended here we have applied the extended linear regressions onto it. Okay, so these things are simple. Extended linear is the optimization type of problem. This is, you can think like it is an optimization problem. Okay, simple, we have to apply this optimization problem on this, that we can easily find. Okay, but the main problem here in the isotonic equations, the main problem here, the hyperparameter that we have to find is the main in Platts calibrations. In Platts means in sigmoidal calibrations, only we have to find the A and B. But here, instead of A and B, we have to find more than. We have to find the A1, A2, A3, A4, and M1, B1, M2, B3. Like that, we have to find it. So this is the main complexity of it. So in isotonic regression, in isotonic regressions or calibrations, in isotonic regressions or calibrations, we need many more points. Actually, we need many more data points or points. Since we have to find more hyperparameter, since we have to find more hyperparameters like A1, A2, A3, like L1, L2, L3. L1 means here M1, B1, it's enough for L1, M2, B2. Just I am talking about this kind of parameter. So because of this, we have to predict more hyperparameter. Because of these regions, we need more data points onto it. Okay, then, but in but in But in flat scaling, but if you think is like a, compare these things like a flat scaling, just in previous video we have discussed. In flat scaling, only we need to predict two hyperparameters A and B. That's enough. We have to predict only two hyperparameters A and B. That's enough. But here we have to predict more than this. Because of these reasons, for isotonic operations, we need large number, more data points because of these decisions. So if we have a large data point, means we have a large cross validation data. Because of that, we have a large calibration data. So it will better we can apply onto it the isotonic regressions. It will better if we apply onto it the isotonic. Okay, but if we have small data, but if we have small small data, that means we have small cross validation data. Small cross validation data, that means we have small calibration data. So for these cases, it will better if we apply the flat scaling. Okay, I think from the discussions you got the point. What is isotonic calibrations and what is its advantage from the flat calibrations? In which situations it will be better to apply? Okay, just say this. I recommend you, if you don't understand, please to recap this video, then it will be better for you. Okay? So just simple idea is if we have the large number of data sets, if we have a billions of data points, so in such cases, it will be better this isotonic. It will better if we apply the isotonic calibration model. But if you have small number of data set, it will be always better if you apply simple the flat calibration model. Right. Okay, I think from the discussions you got the idea. Teach isotonic calibrations and in when which situations we have to apply it and what is the difference it from the flat calibrations. When we discuss the real case study, then you will see these things in more detail.